This short lecture will cover the kinetic theory of gases. First off, we know that particles in all states of matter are in motion. And then we define kinetic energy as the energy of motion. Remember, potential energy is stored energy. Kinetic energy is energy of movement. Okay, so the kinetic theory of gases has three main parts to it. The first is that gases are composed of particles, and these particles are very, 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 very small. They're so small we're going to say their volume doesn't matter, or we can say they have negligible volume. The particles are very far apart. The particles can't see each other, they're so far apart. And in between there's nothing, or there's empty space. Absolutely nothing. Not air, nothing. Because air is a gas made of particles. And then the third point about particles, there are no what we call intermolecular forces. What does that mean? That just means that the particles are not attracted to one another. The second point of the kinetic theory of gases is that particles are in constant random motion. They're always moving, and they're moving at a high rate of speed or a high velocity. They have random paths. It's not like when you walk down the hall on the way to class, you don't have a random path. You walk to avoid people, running into people, or maybe someone you don't want to see. Particles don't have brains, so they don't think like that. They just move in straight lines. So let's also say they're random paths and straight lines. And particles only change direction whenever a collision occurs. The third point of the kinetic molecular theory of gases states that all collisions are elastic. That means that there is no energy lost during a collision. If collisions were elastic, like when two cars collide, no energy would be lost. So when they would collide, they would then go on in a different direction, but still at the same rate of speed or the same total rate of speed. That's not true. So when cars collide, we say that collision is inelastic. But again, gas particles, we consider their collisions elastic. And also, since no energy lost, we can say energy is conserved. Okay, so that brings us to the definition of gas pressure. Gas pressure occurs when particles of a gas collide with an object. They exert a force. That force is called the pressure. We can define pressure as a force per area. The larger the force, the larger the pressure. The smaller the area, the larger the pressure. For example, think about someone that's wearing a hiking boot and they step on your foot with the heel of your toe, the heel of their toe, versus someone that's wearing a high heel and they step on your foot with the heel of their toe. Which one's going to hurt more? The high heel. Why? Because pressure is force per area. The area on the high heel is much lower. That causes the pressure to be much higher, and that gives you more ouch on your poor foot. If there's no gas particle, then there can be no gas particles moving around. If there's no gas particles moving around, then no gas pressure is exerted, and that's called a vacuum. Okay, atmospheric pressure is the pressure that's all around you. you're under atmospheric pressure right now. What is atmospheric pressure? Well, you already know that the atmosphere contains gas particles. Obviously, it contains oxygen needed to support our life. The air is 21% oxygen, and there's also nitrogen. That's 78% of the air around us. There's also argon, carbon dioxide, and other trace gases, like different nitrogen oxides we call NOx, because it could be NO, NO2, or sulfur oxides. Those are pollutions, and other minor things. But those gas particles are moving around and they collide with other objects, like your face. Well, when they collide, they exert that pressure, and that's the atmospheric pressure. As you go up in altitude, let's say we're driving from here, we're about 600 feet above sea level in Cincinnati, to Denver, which is about a mile above sea level. Well, the air thins, and what we mean by the fact that the air thins is that the number of molecules decrease, and this means that the density of the air decreases. Also decreases. And since the number of molecules decrease, the number of collisions are less, so then the air pressure also decreases. We'll talk more about that in the second part of chapter 13. There are several different ways to measure pressure. If you have a barometer in your home, it's more likely actually a manometer. There's one in the class. I'll point out the barometer in the class. It works by having a pool of mercury. So there's this pool of mercury, and then there's a glass tube submerged in the pool of mercury, and some of the mercury goes up into the tube as well. Then there's this empty space. This is a vacuum. The reason you need a vacuum is so that mercury is free to move up and down the tube as needed. If there was air here, as the air got more and more compressed, it'd be harder for the liquid to move up the tube. But the way the barometer in class works, when the atmospheric pressure is high, it pushes down on the pool of mercury, which pushes it way up into the tube. When the level of the mercury goes way up, and we read that level. When the mercury, or when the air pressure is low, so now the air pressure is lower, then the mercury falls. Remember before it was up higher when the pressure was higher because more got pushed up than when it's lower. The units of pressure, there are several. The main one we're going to use in chemistry, the SI unit, is the kilopascal. You will also see millimeters of mercury. That's what the barometer in class units are. Atmospheres, which used to be the old unit of choice. You're more familiar with pounds per square inch if you've ever made sure your tires on your car are well inflated or had to pump up a volleyball or a basketball or a football. Those recommendations are in pounds per square inch. And then torr is an old style unit, not used much today. Conversion factors you need to know. 1 atmosphere is equal to 101.3 kilopascals. That's equal to 760 millimeters of mercury, which is equal to 14.7 psi. Standard temperature and pressure, which we've talked about already, abbreviated STP, just a reminder. And we talked about this way back in chapter 3, so you may not remember, is 0 degrees Celsius or 273 Kelvin and 1 ATM or 101.3 kilopascals.